So how does electricity actually move from a solar panel all the way to your home? Let's find out. To see how electricity is generated and then fed into the grid, let's start by looking at a solar plant. Solar panels generate DC power, direct current, meaning electricity flows steadily in one direction. That's great for electronics, but you can't feed DC directly into the grid. So the first step is conversion. DC power runs through an inverter whose job is to turn it into AC power, alternating current. The same kind of power the grid uses, with a frequency of 50 or 60 Hz. After this conversion, the voltage is still low, typically around 600 to 1200 volts coming out of the inverter. The next piece is the transformer. It doesn't change AC into DC or vice versa, it just steps the voltage up. That low voltage AC is boosted to 20 or 30 kilovolts, allowing it to travel farther with fewer losses. Higher voltage means lower current for the same amount of power. Finally, the electricity flows into the distribution grid. Power entering the grid stays in sync with its heartbeat at 50 or 60 Hz, and high voltage keeps it moving efficiently over long distances. Now, let's look at wind. A wind turbine spins a generator and produces AC power, but that AC is not usable yet. The frequency and voltage depend on how fast the blades are turning, so it's not locked to the grid. Electricity generated from wind has to run through a power conversion system. The raw AC power from the turbine is first turned into DC and then back into clean AC at 50 or 60 Hz, synchronized to the grid just like we saw with solar. After that conversion, the voltage is still in the hundreds of volts, roughly in the same range as after the solar inverter. Then the transformer steps that AC up to tens of kilovolts so it can flow efficiently into the distribution grid. The key difference from solar is that solar starts as DC and needs an inverter before electricity enters the transformer. Wind starts as AC, but it's unstable AC, so it still needs a power conversion system to create grid quality AC before it can join the system. Next, let's look at how conventional power plants feed electricity into the grid. Gas, coal, nuclear, or hydro plants spin a generator that produces AC power directly, already locked to 50 or 60 Hz. Because the generator itself rotates in sync with the grid, no inverter or power conversion system is needed. The voltage leaving the plant is already high, typically between 10 and 25 kilovolts. And then a transformer steps it up even further. Depending on the plant size and location, that electricity can feed directly into the distribution grid or be stepped up to 110 to 400 kilovolts for long distance transmission. Unlike solar or wind, these traditional plants already produce grid synchronized AC, ready to feed directly into the system. Now, let's look how battery storage systems interact with the grid. The grid delivers AC power at 50 or 60 Hz. A transformer steps that down to a lower voltage. The power conversion system, a bidirectional inverter, then converts that AC into DC so the battery can charge. Later, the process runs in reverse. The power conversion system turns the battery's DC back into clean, grid-synchronized AC and sends it right back into the grid when it's needed most. Finally, let's look at how a battery pairs with a solar plant. Solar panels generate DC power, which can take two paths. It can go straight into the battery for storage, or it can be sent through the power conversion system to be turned into AC and exported to the grid right away. Later, the process can reverse. The battery discharges its stored DC energy and the power conversion system converts it back to grid synchronized AC, sending it through a transformer into the distribution grid. This setup allows operators to shift solar energy from midday to evening, storing excess energy when generation is high and releasing it when demand peaks. So whether the power comes from solar, wind, or the grid itself, everything ultimately flows through the same system, converted, synchronized and balanced to keep the lights on.